All right, what I want to do in this video is I want to use the differential equation that models logistic growth to derive the population function that we get, the population function that we use in logistic growth cases. So this is not absolutely necessary to our understanding of logistic growth models, but I think it's a pretty clever proof, and it also gives us a good understanding that of why we're getting our population function, why it looks the way it does, and that it's not just a random assortment of numbers and values. And it's also a good review of solving differential equations, which we've practiced this chapter. So let's start with this differential equation. Again, this is the differential equation that models logistic growth. And a couple of things about this that I should highlight before we start. First off, we should know that P is a function of some t value, or that is to say time. And we should also know that K and M are constants, which is going to help us when we're doing some integration and later on in this proof. So let's start here. So we've got a differential equation. We know that our first step is to separate our variables whenever we're solving differential equations. So we're going to go ahead and we are going to move all of our quote unquote P terms to one side and non-P terms to another side. So I'm going to go ahead and divide both sides by P times M minus P here. So I'm going to write this as 1 over P times M minus P. And this is with respect to P. And over here on this other side, we've just got our constant K, and we're going to go ahead and write dt here, okay? All right, now next up, we're going to go ahead and now that we have our variables separated, we're going to go ahead and integrate both sides. All right, so let's go ahead and do that. We're going to integrate both sides. And actually, you know what, before I integrate, it might be a good idea for me to actually rewrite that left side. And don't worry too much about how we're doing this, but actually using partial fraction decomposition, I can rewrite my left side so that it would be the following. 1 over m times 1 over p plus 1 over m minus p. Again, all of this with respect to p. And if you want to pause and work that out and just check to make sure that these two steps are indeed equivalent to one another, you're welcome to. Or you could take my word for it. It's up to you. I don't know how much of your trust I've established at this point in the course. This right side here, if I go ahead and integrate that right side, since that side was pretty much already ready to go, I'm going to get k times our variable t, because we're integrating with respect to t now, plus some constant c, okay? And I'm just going to write here that we wrote our left side using partial fraction decomposition, just as a reminder as why we were able to write that. All right, so with the reminder that m is a constant, I'm actually going to move this over to the outside. So I'm going to write this 1 over m. And again, I'm integrating 1 over p plus 1 over m minus p, all of this with respect to p. And I'm going to bring my right side down, okay? And now we're ready to integrate. So we've got 1 over m here, and I'm integrating 1 over p. So we know that that is the natural log of the absolute value of p minus the natural log of the absolute value of m minus p is equal to kt plus c, okay? And I'm going to now use a log property, which we've done throughout this chapter, to rewrite this as the natural log of the absolute value of p over m minus p is equal to kt plus c. And again, if you're not sure why, this was just a log property, okay? And I'm actually going to use another log property now, because now I can actually rewrite this as the following. I got 1 over m. Now, if I were to take this entire argument over here and rewrite this to the -1 power, okay, then we know that this is equivalent to the reciprocal of this. Okay? This is the reciprocal of this. Well, this m minus p over p. Now, in order for me to do that, I would move this to this side here and write this as -1. Well, where does that -1 go? Or how am I allowed to multiply by -1? Well, if I also do that to the other side. So all that to say, I can rewrite all of this here as negative kt minus c. And just to recap how I'm able to say that, because we know that the natural log of 1 over a is equal to the negative natural log of the absolute value of a, something like that. Okay, so I'm just using another set of log properties here to kind of leveraging being able to use negative powers to write the reciprocal there. Well, Now that we have all that, I can now move this coefficient here and rewrite it as a power of our argument. So natural log of m minus p over p, all of this to the 1 over m power. And this is equal to negative kt minus c again. Now, I'm going to exponentiate both sides. I'm going to rewrite these so that they are the powers of e, okay? And we know that again, after we've exponentiated, and let me just write that, so we know exponentiate. Well, now what do we have? We know that e raised to the natural log of some argument is just that argument itself. So we have m minus p over p to the 1 over m power, okay, is equal to, and we've done this numerous times throughout this chapter, I'm going to write this now as c times e to the negative kt, and then since I'm introducing this new constant here, let me actually rewrite this as c sub 1, okay? And I'm going to let this big C here be equal to not only e to the negative c power, c sub 1 power, but I'm going to do that plus or minus so that we can take care of that absolute value, right? So that we can rewrite the absolute value there. So I'm going to write c here, and then this absolute value I can now just write as just parentheses, m minus p to the 1 over m power, okay? Now, this next part may not be super intuitive, but what I'm actually going to do is I'm going to take all of this, and because I want to rewrite that rational power here, I'm going to raise this to the m power, which means I also need to do the same thing to this side. So, I know this is getting a little gnarly looking, but it's going to get cleaned up real quick. We've now got m minus p over p is equal to our big C, or our big constant, times e to the, now we're raising all of this here to the negative kmt power, okay? So this is going to be negative kmt. Well, from here, we're going to just do some rewriting. This is m over p minus 1. This right side here is c times e to the negative kmt still, okay? This I can write as m over p is equal to c times e to the negative kmt plus 1. That means p then is equal to the following: m over all of this, 1 plus c times e to the negative kmt. And there you have it. There's derivation there. Now, one last note before I close it up. Just want to highlight here, ask yourself, what does c represent? Well, it's really from this part here, because this is a question I get from students all the time. What is c? Well, when t is equal to 0, ask yourself, what is this equal to when t is equal to 0? Well, when t is equal to 0, c is effectively just equal to, when t is equal to 0, all of this is equal to 0. E to the 0 power is just equal to 1. So c is just equal to m minus p over p. That is to say that c is a constant which represents the difference, or the ratio between the difference in our carrying capacity and our initial population, and that initial population itself. So hopefully this video kind of gives you a good sense of the proof for the logistic growth function.